Okay, so welcome again to Chemistry 101, and today we're going to talk about enthalpy. So enthalpy, we are going to consider two situations here, where we have a constant volume where delta V is zero and a constant pressure where delta P is zero. Enthalpy is a thermodynamic quantity used to describe heat changes taking place at constant pressure. So an enthalpy is actually defined as H is equal U plus PV. So there is nothing called enthalpy, it's just something that scientists came up with. We know there is something called internal energy, we know what pressure is and volume is. So the combination of U plus PV is what we call H or enthalpy. So enthalpy is defined in terms of these three things. So now, if you consider a change in the system, if you want to consider a delta H, that means a system that is going from state A to state B, then in that case, delta H is equal delta U plus delta PV, and we're going to take two cases here where the pressure is constant or the volume is constant. So just remember this, that H is equal U plus PV, or delta H is equal delta U plus delta PV. Now, the two situations that we are going to study today is that we have a constant pressure or a constant volume. When the pressure is constant, that means there is no change in the pressure in the system, and delta P in that case is equal to zero. And the other case is we have no change in the volume. That means the volume, you have a container with a constant volume. So V final is equal to V initial. In that case, delta V is zero. Now, let's prove that a very important rule in thermodynamics, which is delta U is equal QV. Now, if you start from the first law of thermodynamics, which is delta U is equal Q plus W, we know that. At constant volume, actually there is no work done, because the work, as we know, it's equal minus P delta V. That's the rule of the work. When delta V is zero, that means you have a fixed rigid container, a container with rigid walls, let's say a cylinder, a gas cylinder made of steel, and the volume does not change. In that case, delta V is zero, and there is no work because W is minus P delta V, and therefore W is zero. So if you plug this into the original equation, in that case, that will give you delta U is equal Q plus zero, because the work is zero, and I just change Q into QV, indicating that we are working at constant volume. Then we come up to this very important relationship in thermodynamics, which is delta U is equal QV. That's something we always need to remember. So if you are measuring a Q in the lab, and that measurement is done under constant volume, then that quantity Q is equal to delta U. That's a very easy way to calculate the change in internal energy of the system. Let's prove another one, which is delta H is equal QP. This one is a little bit more difficult to prove, but it's okay. But let's go over it. Now consider a system open to the atmosphere. That means we have a constant pressure. If you are doing something in the lab, or you're boiling water or anything, actually you are working under constant pressure, because you cannot change the atmospheric pressure. The atmospheric pressure is fixed during the day at least, and therefore you are working at constant pressure. So we are starting again with the first law of the thermodynamics, which is delta U is equal Q plus W. Again, the definition of work is minus P delta V. Okay, and here there is work. The work is not zero, so we have a value of work. We plug in this into the equation, so delta U becomes QP, that indicating we are working at constant pressure, plus minus P delta V. Let's call this equation number one. For the other part, we've taken the definition of enthalpy, which is delta H is equal delta U plus P delta V. And we're working at constant pressure, so that's P delta V, not delta PV. And we're just gonna that will give you equation number two. If you notice here that we have two equations, 1 and 2, I am going to substitute equation 1 into equation 2, and that will give me delta H is equal QP minus P delta V plus P delta V. So these two terms will cancel, and you can come up to this equation, delta H is equal to QP. Now, the derivation is not required from you, it's just for you to understand, but you need to memorize that delta U is equal QV and delta H is equal QP. These are very two important equations in this chapter. Now, for reactions, chemical reactions, most reactions actually occur at constant pressure. And that's why we are interested in delta H, because delta H is equal QP. So the heat that we are measuring in the lab, if we are measuring this at constant pressure, that will equal to delta H. So this is one way to measure delta H for the reaction. And that's the first thing. That the other thing is that delta H for a chemical reaction is actually can be calculated as follows. It's delta H, it's the enthalpy of the product minus the enthalpy of the reactants. And therefore, delta H itself can be negative or positive, can be exothermic or endothermic. So if the enthalpy of the products is bigger than the enthalpy of the reactants, you will have a positive delta H. And if it's the other way, you will get a negative delta H. And I'm going to explain this in the next slide. So if the enthalpy of the product is bigger than the reactants, then you have endothermic reaction. That means delta H is bigger than 0. And if the enthalpy of the reactants is bigger than the products, then you will have delta H exothermic, which is negative. No, the proof is not required. Yes, I can. The proof is not required. It's just you need to know these relationships. Now, there is no pointer here. I have to react to, yeah. So I have already explained this before, but for endothermic reaction, an example of that is solid water goes to liquid water. So the melting is endothermic. Endothermic, that means the system needs energy, needs heat to do that. You need to supply heat for the system to be endothermic. In this case, as you see here, the reactants are the H2S, H2O solid, and the products is the H2O liquid, and therefore the products has higher enthalpy than the reactants, and this is what endothermic means. The other way is exothermic. It's the exothermic. Let's take an example of the combustion, the reactants of methane. So the reactants is methane plus oxygen, and this is going to produce UCO2 and H2O. In this case, the products have lower enthalpy than the reactants, and this is what exothermic means. Okay, exothermic means the enthalpy of the products are lower than the reactants. Okay. Some questions here. Okay, yes, I am recording the lecture. So guys, I just want to tell you something here, that we have exothermic and we have endothermic. So in exothermic, you have reactants here and products here. So the reactants are higher in enthalpy than the products. In endothermic, it's the other way. So delta H for exothermic, it's the enthalpy for the products minus enthalpy of the reactants. Same thing here. Delta H is equal enthalpy of the products minus enthalpy of the reactants. And if you notice the exothermic, the products have lower value than the reactants, and that's why you get negative here answer. So negative is always exothermic. And for the endothermic, the products have higher values. Let's say the product is 100, the reactant is 50. So 100 minus 50 is 50, and that will give you a positive number. So in exothermic reactions, that's very important to mention, that products have higher energy or higher enthalpy, and this one, the reactants have lower energy. Higher energy means lower stability. That's very important. So in exothermic reaction, the reactants are less stable than the products. In endothermic reaction, the reactants have lower energy, so they are more stable. than the products. In this case, the products will be higher in energy and less stable than the reactants. Okay, so just keep this in mind when you study. Let's go back to our PowerPoint here. So we defined the enthalpy and we considered both cases at constant pressure, at constant volume, and we talked about what is exothermic and endothermic. Now, in thermochemical equations, it's very important to know that the stoichiometric coefficients actually play a role. So here, when I say H2O solid goes to H2O liquid, delta H for that is endothermic, it's at about 6.0 kilojoule per mole. Now, what is kilojoule per mole of what? I read this as a kilojoule per 1 mole of water. Okay, so this is how you read this question. Now, if you flip this reaction, if you reverse it, you reverse the delta H. So delta H, if you want to flip a reaction, so H2O solid goes to liquid. If you want to flip that and become liquid to solid, then delta H will be minus that number. Okay, and that means the delta H of melting of water is 6 kilojoule, but delta H of freezing of water, which is the reverse of melting, that would be minus 6 kilojoule. Now, if you want to decide at one point to multiply an equation by a factor, let's say you want to multiply this equation by 2, so it becomes 2H2O solid goes to 2H2O liquid, then in this case delta H will be 2 times that number, so 2 times 6 is 12 kilojoule. So remember that when you solve questions. The physical state for all reactants and products must be specified in a thermochemical reaction. So for example, it does not make sense to say that H2O goes to H2O and delta H is 6. No, what does that mean? You have to put the physical state, solid, liquid, gas, whatever, next to the reactant or the product, because a delta H is specified for a specific reaction, and this physical state should be mentioned. So as you see here in this question, for example, any question in the book, it's always the physical states are mentioned. So 2SO2 gas plus O2 gas goes to SO3 gas. So the G or the L or the S should be mentioned. Now let's see what this question is asking. Given the thermochemical equation, 2SO2 plus O2 gas goes to 2SO3 gas, delta H is minus 198.2 kilojoule per mole. Calculate the heat evolved when 87.9 grams of SO2, molar mass is 64.07 gram per mole, is converted to SO3. So to solve this question, so 2SO2 gas plus O2 gas goes to 2SO3 gas. This question says delta H is equal to minus 198.2 minus 198.2 kilojoule per mole. Now per mole of what? This question, the way I understand it is that it's kilojoule per mole of oxygen, because oxygen here is the only one that has one coefficient. So if 1 mole of oxygen is reacting, that value minus 198.2 will be produced. If 2 mole of SO2 is reacting, then minus 198.2 will be produced. If 2 moles of the SO3 is produced from this reaction, minus 198.2 kilojoule will be done, and so forth. Now, if you are reacting 1 mole only of this, then delta H will be half of that number. So I hope you get the idea here. So per mole, that means per mole of the oxygen. We have 87.9 gram of SO2. So 87.9 gram. And the molar mass is 64.07. So 64.07 is the molar mass of this guy. Now he needs to find delta H if I'm reacting 87.9. Now from this I can find the number of moles, of course. Number of moles of SO2 is equal 87.9 gram divided by 64.07 1 gram per mole, and that should give you the mole value. That's 1.372 mole. Now there is a rule that you should know from now on, that delta H is equal N delta H molar. That's a very important rule in this chapter, where delta H is the enthalpy and delta H molar is the molar enthalpy. So delta H here is measured in kilojoules or joules, and this one is in kilojoule per mole. So that's the difference of them. Okay? So delta H is equal N delta H molar. So in many of these questions, it's asking you for delta H, giving you delta H molar, or the other way around. In this question, he is providing you with the delta H molar, because it's in the kilojoule per mole, and he's asking for delta H. We have calculated the number of moles, so in this case, we just say the delta H, the one we need, is equal N delta H molar, that means 1.372 mole multiplied by the minus 198.2 kilojoule per mole. So you see here the mole goes with the mole, and you just multiply these numbers. You multiply minus 198.2 times 1.372, and the answer will be minus 136 kilojoule. So the answer is minus 136 kilojoule, not kilojoule per mole, okay? Sorry for the bad writing, but this is how you do it. Anybody has any question on this? Anybody has anything on this question? So Lina, we cannot multiply reactants by a number and the products by a number. When we multiply the equation, we multiply the whole thing with a factor, okay? You cannot multiply just one side of the equation. The first step, I'm just calculating the number of moles. So in the question, I'm giving grams and a molar mass. So the number of moles is mass divided by molar mass. I'm just calculating the number of moles. So it's grams divided by gram per mole. Okay? Sure. Okay, so let's switch back to our PowerPoint again. So now, let us compare delta H with delta U. Now let's consider the reaction 2 sodium solid plus 2 H2 liquid goes to 2 NaOH plus H2 gas. Delta H for that is minus 367.5 kilojoule per mole. So this is the molar enthalpy. Now this is enthalpy, it's not internal energy, and internal energy is not equal to the enthalpy, okay? So because you know delta H is equal to delta U plus P delta V. That means delta H is not the same as delta U, but let us compare the values of these two things for this reaction. Now, if you rearrange that equation, you come up to that delta U is equal to delta H minus P delta V, okay? Now, at 25 degrees Celsius, the volume of 1 mole of hydrogen is equal to 24.5 liter, because this is it's not STP, but you can calculate actually that the 1 mole of hydrogen gas is 24.5 liter, and this is the only gas in this equation. Everything else is not gas, it's solid and liquids and aqueous. So the only thing that is gonna do work in this case is the hydrogen gas. Let's calculate the work of that, or actually let's calculate the P delta V for that. So P delta V, if this reaction is happening, it's going to produce some hydrogen. The hydrogen will increase the volume of that container, right? And therefore, P delta V is 1 atmosphere, which is the constant pressure, times 24.5 liter. And we're going to get to an answer 24.5 atmosphere liter. We convert that to joules, 2.5 kilojoule. So in that case, delta U is equal to delta H minus P delta V, which is minus 367.5 kilojoule per mole, minus that value, and you will have minus 370. So delta H is minus 367 and delta U is minus 370, and therefore you see a small difference here between delta H and delta U. Now, we're gonna come up, actually, I will teach you how to also, there is an easy way to do this. If you start with this equation, delta H is equal delta U plus P delta V, you can rearrange the equation to delta U is equal delta H minus delta PV. And we know that PV is equal in RT from the ideal gas law. I'm just substituting that delta U is equal delta H minus delta nRT. And because the temperature here is constant and the R is constant, I'm gonna change that. This will give us delta U is equal delta H minus RT delta M, where delta M actually is the change in number of moles of gases. So now we have another equation here. It's a very important equation. Minus delta nRT. This is a very important equation here, that you can calculate actually delta U from delta H or vice versa. And delta N here is defined as the change in number of moles for gases only. If you have gases in the equation, you can consider them. Otherwise, you don't consider them. Okay, so delta U is equal to delta H minus delta N RT. And therefore, if you go back to this equation here, the one we've been talking about, which is 2Na solid plus 2H2O gas liquid goes to 2NaOH plus H2. So delta N for this reaction, it's the number of moles of the gaseous products minus number of moles of the gaseous reactants. There is no gas in the reactants. There is 1 mole of gas in the products. So therefore, delta N is equal to 1 minus 0, and it is equal to 1. And in this case, here, we can solve the questions. I'm going to solve this question based on this. Now, in this question, calculate the change in internal energy when 2 moles of CO are converted to 2 moles of CO2 at 1 atmosphere and 25 Celsius. We have a reaction that appears, everything is gas here, and we are provided with delta H, which is delta H is equal to minus 566 kilojoule per mole. So in this case, we apply our equation. So just maybe keep this PowerPoint open in your computer so we can see it. 2CO plus O2 gives 2CO2 gas, and you are provided with delta H. So let's open our whiteboard here and solve the question. So the question says 2CO gas plus O2 gas goes to 2CO2 gas. Delta H is equal minus 566 kilojoule per mole. Now I'm asking for delta U. Is delta U is equal to delta H? No. Delta U is not equal to delta H. We have to calculate that. We have a relationship that delta U is equal to delta H minus delta N RT. So delta N here is the number of moles for the gaseous products minus the number of moles of the gaseous reactants. Everything is gas here, as you see in the question. So you have in the products we have 2 moles because they are a gas, minus 3 because you have 2 moles of CO2 gas in the products, that's 2, and you have 2 moles of CO2 gas and 1 mole of O2 gas. They are all gases, so there are 3 moles of gases in the reactants. And 2 minus 3 is minus 1, and of course you keep this as minus 1. Now R here, you cannot supply this 0.08 atmosphere liter. That's not gonna work here. You have to use the value of R, which is 8.314 joule Kelvin minus 1 mole minus 1. That's the value of R that you must use in these questions. You cannot use the other value, the one we used in chapter 5. We need the value that is in joule, because this is gonna work out, okay? We need also to change delta H into joules. This is in kilojoule, we have to change to joules. So that answer, so delta U will be equal then in that case, 566 kilojoules, so that's minus 566 times 10 to the power 3. I have multiplied this by I multiply this by 1000 to make it in joules, minus, now delta N RT, delta N is minus 1, times R, which is 8.314 joule Kelvin minus 1 mole minus 1, times T, which is 25 Celsius, that's 298 Kelvin. You must also change the Celsius into Kelvin, and that's mentioned in the question. He said calculate delta U as 25 Celsius. So we get everything we need here. Just make sure that to change the kilojoule into joules, and you use the correct R value. If you do the math here, you will find delta U to be equal minus 565, minus 565 kilojoule per mole. The answer will be in joules into kilojoule. You see here the difference between the delta H. When you do these questions, the difference between delta H and delta U is not that big, by the way. It should be close to each other. Okay. Now there is a question that I always ask my students about, which is, when does delta H equals actually delta U? When does delta H is equal to delta U? Well, let's look at the mathematics. Delta U is equal delta H minus delta N RT. There are cases where you have delta H is actually delta U when this term is equal to 0. When this term is 0, that means we are working at, well, R cannot be 0. Temperature could be 0 Kelvin, yeah, so that's the first case, one at 0 Kelvin. So when the temperature, which is not possible anyway. So at 0 Kelvin, delta H is equal to delta U. But the most important is that when delta N is equal to 0, that means for reactions, there is no change in the number of moles. So if you have 2 moles of gas, it goes to 2 moles of product, so 2 minus 2 is 0. In this case, you will have a situation where delta U is equal to delta H. Or for reactions that involve solids and liquids only, that's a situation where you have delta H is equal to delta U. Because when you have solids and liquids, there is no gas, and therefore delta N is defined only for gases. So you have a reaction, let's say something solid goes to something liquid. In that case, delta H is equal actually to delta U in that case.